So it's a pleasure to announce the last speaker of today, Subir Sachdev, and he will talk about crossover from a fractionalized SYK spin liquid to a confining spin glass. Please go ahead.
Okay, well, thank you very much. And sorry I can't be live at the meeting, and but I hope you're enjoying the beautiful environment and the good weather. So I'll be talking about some work which is in this preprint that just appeared on the archive with Maine Christos, who's a graduate student at Harvard, and Felix Hale, who's a postdoc at IAS. All right, so just want to a brief commercial announcement. There's a review article that I've written in collaboration with Debanjan Chaudhry, Antoine George, and Olivier Parcollet on basically applications of the SYK model to condensed matter physics, but there's also a section on the gravitational connections. All right, so I'm going to be interested here in the instability of the SYK model in the context of models that are realistic for condensed matter applications. And this instability has been known for a while, and it leads to spin glass order. And then so I'm going to present some progress in understanding this instability. And then towards the end, since I'm at a string conference, I will argue that there are also some interesting connections to things that have been discussed in holography and black holes, in particular the old idea of ADS to fragmentation. Okay, so let me just begin, however, since perhaps many of you are not familiar with spin glasses, with the basic spin glass model. So this is the simplest version of it is the Sherrington-Kirkpatrick model, where you just have n sites and binary variables, sigma I, on each site is a classical bit, and there's some energy function of these classical bits with random couplings Jij. And we'd like to evaluate the partition function with different random Gij. Okay, every spin is coupled to every other spin. All right, so this model is known to have a phase transition as you lower the temperature. There's just some random thermostat at high temperatures, but then there is a freezing of the spins into a multiplicity of possible spin glass states. So what happens in this spin glass state is that each spin acquires some random expectation value. So if you were now looking at an ensemble of systems, then it's very, and then you averaged over site, you just still get zero because the average over sites will give you different values of sigma I, which vary in sign on different sites. Of course, in a ferromagnet, they'll be the same, and the antiferromagnet, in a spin glass, they're completely random. So the Edwards-Anderson order parameters, you take the square of this object before averaging over systems. And this order parameter is 0 here and non-zero in the spin glass phase. Okay, so then in honor of the recent Nobel Prize, let me just quickly summarize Parisi's solution for this model for understanding the structure of the spin glass phase. So the basic trick is to introduce replicas, which was actually already introduced by Edwards and Anderson earlier. So you take n copies of the system, little n, and then you take the average after taking n copies. And then you can show that the actual averages you're interested in appear in the n tends to 0 limit. Okay, so once you take the average of the partition function, then this is what you get, where the different replicas are coupled to each other. But there's a beautiful simplification here that the sum over I appears inside the square bracket. So there's a sum over I here, and it's only the nonlinear terms are only associated with the sum inside. So therefore, you can introduce an auxiliary variable, little QAB, so that when you do the integral over QAB, you get this term back again. And now the sum over I completely disappears because the sum over I is the same on every site. And therefore, this thing appears to the power n. And that's the important point. So now you just have some finite sum to evaluate here. For each QAB, sigma A is plus or minus 1. So there's n squared variables, little n squared, which is going to go to 0. And that's, of course, the subtlety. But you can take the large n limit immediately and just look at the saddle point of the Q integral. So therefore, all you have to do is to look at saddle points of this free energy functional. It's a free energy functional of a little n by little n matrix. And this is the explicit functional. For n equals 2 or 3 or 4, you can write it out. Just a sum over 2 to the n terms in here, where n is small in principle. Okay, and what Parisi understood was the solution of these saddle point equations that lead to a stable solution at low temperatures. And so there's a lot of complications there having to do with the structure of this matrix QAV, which Parisi is characterized. It breaks replica symmetry, so it's not just equal to the same number for each A and B, not equal to each other. It's characterized by a function called a Q of U, sometimes called a Parisi function. And the Edwards-Anderson autoparameter is the value of Q at 1. So it goes between 0 and 1. So the task for us to fully characterize the spin glass state is just to find this function Q of U, which describes the saddle point of this very simple looking function. And that will tell you all the thermodynamic properties you need to know about the spin glass state for this model. Okay, now that's not an easy task, and Parisi first solved it, and now we have rigorous mathematical proofs that his solution is correct. But it involves, some highly rigorous steps of non-rigorous steps where you, at least initially, where you take first little n to infinity, and then you send it back to 0 when you analytically continue. Okay. Anyway, but fortunately, for the more problems I'm considering, we won't have to deal with this complexity. We'll just have to, you can borrow this Parisi solution where we need it and won't change in structure very much. Anyway, okay, so now let's imagine we make this a quantum. So one easy way to make it quantum, which is what was done in the 90s, was to add this term sigma xi. So this is a transverse field, and it causes tunneling between the two states. So now this is a quantumizing model, and it's got another axis, which is G, which is the strength of the transverse field. The classical model was G equals 0. And this model is actually now also thoroughly understood. And you get now a spin glass state for a finite region of GC. And the structure of the spin glass state, at least of the spin glass autoparameter, is identical to that in Parisi's solution, and that I'll describe in a minute. And reason for that I'll describe in a minute. Okay, so now what happens when you try to extend the solution of the SK model to this quantum model? It's a little bit easier to just replace this Ising variable by a real field at the cost of some potential V of phi, which is minimum at phi equals plus or minus 1. Let's just do that, but the same results apply for this model too. So you have a particle with some potential V of phi, and if you follow through Parisi's method, what happens is that this matrix Q, little QAB, is now replaced by another matrix, capital QAB, but that matrix is a function of time. So now you have not just one n by little n matrix, you have a function which takes values on n by n matrices of time. And now you have to look at this saddle point solution. So that's quite a complicated problem, but it has been fully sorted out already in the early 90s, and we understand the basic structure, which is structured in this phase diagram. And what's the reason for the simplicity? The simplicity is that there's another limit where this model becomes very simple, which is when G goes to infinity. So if G goes to infinity, then the spins all point in the X state, X direction. That's the unique ground state, and so we call it a trivial state, and all excitations have a gap. So there's a trivial state at large G, and then as you're approaching decreasing G, you can simplify near GC. And what you find that the theory here near GC fully matches the theory at G equals 0, and so you're pretty sure you've got everything right. But let me also show you, but now that you have this whole function to deal with, now we have two different characterizations of the spin glass autoparameter. There's the A not equal to B case, in which case, in fact, this object has to be time independent. Now, you may have seen replicas in wormholes in these days where this off-diagonal term is also time dependent. I think that has to do with the fact that you're not taking the n goes to 0 limit in those cases. Here in the n goes to 0 limit, this thing just factorizes, and these quantum averages are obviously time independent. And therefore, so this function, the off-diagonal components are just Parisi function. But you also have the diagonal components, which is this function q of tau. And so now you have a quantum handle on this correlation, on this Edwards-Anderson order parameter. It's given by the long time limit of this function at 0 temperature. So there's two different ways of getting it. And they both have to agree. And this is something, and that's another consistency check on the whole theory, that all does agree. And yeah, so the whole formalism makes sense, and the simple phase diagram is fine. All right, so now finally, let's turn to the model. So this is all work done in the early 90s. In fact, just before we started looking at a different model, which is the model not with Ising spins, but with SU2 spins. Actually, the most important difference here, you don't even need SU2 symmetry. The most important difference here is that there's a Kramers degeneracy on each side, which the Ising model in the transverse field does not have. So we're going to take this model, just like Parisi's model, but replace sigma I, sigma j by quantum spins. So they obey this Heisenberg algebra. S squared is 3/4. These are the spin-and-a-half spins, and j squared, j squared. So that is exactly the same model, but with quantum spin-and-a-halves. Now, the key difference here, in contrast to this model here. So this model, if I just put jij equal to 0, I have two levels on each side, and then there's a degenerate ground state, which is non-degenerate ground state, which is sigma x equals +1. And that's a non-degenerate state. On the other hand, here, if I put jij equal to 0, each site has an exactly degenerate ground state. And that's really the key difference. So that leads to all kinds of differences and leads to all the SYK physics that we subsequently worked out. All right, but we turned the same crank for this model as we turned for the Parisi model. And now the important difference is that because of the degeneracy on site, there is no trivial state possible. You could lose the spin glass order, which is what we were trying to do at 0 temperature. And what we found is that you can a possible gapless state, which in fact features fractionalization and deconfinement, which has a power law decay of correlations. It's not a trivial state at all. In fact, that is the SYK state, or a spin glass state, okay, where this correlation function goes to finite value, non-zero value, as tau goes to infinity. And similarly, there's two different characterizations of the spin glass order parameter. All right, so what is the action here? Well, it's exactly the same thing. You have this q squared term, just as you had in all the three models I've talked about so far. And then you have a path integral of a single spin with a replica index, which has a self-interaction with QAD. That's also very, very similar to what we saw before. In the classical limit, you can just do the integral, everything becomes time independent, and you're back to the classical model. The quantum product here is this term. Now, because of degeneracy, you have a Wess-Zumino-Witten or a Berry phase term. And this is what's responsible for all the novel physics. So this is just the term which, as the spin is moving, this vector S is moving on a sphere, you pick up a phase vector, which is the area enclosed by the path, times 1/2. That's for spin a half. Okay, so how do you solve this problem? Well, this is a hard problem to solve. It's still not solved today in any fully reliable manner. The one method that's worked very successfully, which I'm going to exploit today too, is the 1/mx, large M expansion. So this is the problem is right here. This is the problem we want to solve. Everything I'm going to talk about is the solution of these saddle point equations. Find the saddle point of S of Q, where ZF of Q is this function. That's the problem I'm addressing. Everything else is about this problem. Okay. So that's the way. First thing to do is to write this thing down. I'm sorry for the many equations here, but the basic idea is very simple. You take that path integral and you rewrite it in terms of these fermions. You represent the spin in terms of these fermions, where these fermions have a constraint. And the path integral over S is then exactly the path integral over fermions, but the fermions have the usual linear and time derivative action. And then you can take the large N equations still for any M. M is the SUM here. And that reduces to now things that look somewhat more familiar in the context of the SYK model, where you get the G sigma theory, but really what you get is the G sigma Q theory. You have these G and sigmas of fermions, and then you have the QAB, which is the spin glass order parameter functional. All right, so this is still too hard for any M, and what the rest of the talk is about understanding the 1/, structure of the 1/n expansion of this theory. So what led to the original paper on the SYK model was taking the large M limit of this model. M goes to infinity of just this as defined, but we're interested for any finite M. Then the large M saddle point give you these equations, which still have all these replica indices floating around. But then we made the important observation that this fermion Green's function cannot be replica off diagonal. And the reason is simply that a fermion cannot condense. So a single point function of the fermion has to just vanish in every state. And therefore, this G can only be replica diagonal. And so then everything simplifies. And these are the original SYK, these are exactly the SYK equations obtained in this double scaling limit of N goes to infinity followed by M goes to infinity. But these are one important difference though between the SYK model and this model is that these are equations for particles that are fractionalized. These are equations for these fermions, which are just fractions of a spin. In particular, there's a U1 gauge symmetry here. If you rotate the F's by an arbitrary phase factor, it doesn't change S. That's not true in the SYK model, what's called the SYK model. There is no emergent gauge symmetry there. But here there is, and that changes many of the properties that I'm going to discuss today. Okay. So anyway, so these are the SYK model and equations, and now, of course, we understand a great deal about them. Let me just plot one of the things we now know in amazing detail. This function Q of tau now is fully replica diagonal, so there's just one function to determine. You don't have to worry about any of the Parisi stuff. This is a very different problem. And now we know a lot about it. So this is just the spin-spin correlation function. And its spectral density decays as 1/tau at long time. And this means that the spectral density goes to a constant as a function of omega. Then the first term is a omega term like this linear and omega term. And that term, so this sine omega we already had in 93. This term only understood recently, and this comes from the boundary graviton operator. It's the Schwarzian action that in the spin susceptibility at large N gives you this correction. And all of this is present both for the SYK and this spin model. Okay, so this is and the red line is the numerical solution of the SYK equations, and the dashed line is this particular expansion that we've determined in this paper. Okay. All right, so that's a review of then. Yeah, I've already said that. So I've now told you about the spins with random change. And now, and what we found is a solution which is very, very different from the Parisi solution of the spin glass because of quantum effects, but this is in the large M limit. And so what we want to do is now look at this numerically. So we go back to SU2 and solve this numerically, which was already done earlier by Rosenberg and Arakia. We did it part of a more extensive study of the doped system, which I will very briefly mention. But for this particular model, here's the result for SU2. So just to remind you what we're presenting effectively, although that's not how we became the results, here's this problem. We're just solving these equations by some numerical method for SU2. In fact, the way we solve it is the exact diagonalization of the lattice model. But anyway, this is formally we're just solving these saddle point of these equations. Okay, so you can solve those equations, measure the spin-spin correlation function, and what do you get? Well, you get this green line. Okay, this is for a finite system of about 20 spins, and there's actually another paper which has done it by actually solving those equations. Those equations not easy to solve because of the sign problem, all these Berry phase terms. So what do you see? Well, first of all, you see this big peak, which actually becomes sharper and bigger as you increase the system size. And that peak is basically telling you that you have some very low frequency spin fluctuation, whose frequency becomes slower and slower as you make the system larger, and that's exactly what you have in a spin glass. The spins are freezing and remembering their orientation in some random direction. So that's the spin glass order, which is not present in the SYK solution. However, if you look at the higher frequency part, it's actually not a bad match to the red line, which is what we obtained from the large M limit. There's one parameter that we rescale, but that's it. But the general shape is the same, and also this linear behavior and the discontinuity are believed to be exact exponents in all orders of 1 over m. Anyway, so that's an encouraging sign that even for SU2, there's at least a finite experimental window where you have the spin liquid behavior appear, and clearly visible. And the strength of the spin glass order is around 0.02. It's very weak. Okay. All right, so that opens up the problem we started to address, the crossover. Can we now understand what's going on? Can we at finite m as you go to lower and lower frequencies? We understand the behavior at higher frequencies for SU2. That's the SYK spin liquid, and at numerics we see there's a spin glass. So this is the work we've done recently with Main and Felix, and so this is the theory I wrote down earlier. Forgive the complexity, but really it's just the same bag of tricks that we started with the Edwards-Anderson model, except generalized to things that depend on time. And so what we do is we take this QAB, which in the large M limit was just Q of tau, and then we perturb it a little bit because we believe the spin glass order is weak. In particular, the off-diagonal components are 0 to begin with, so we add some off-diagonal component. And then we just expand this in 1 over m expansion, or actually not even 1 over m, in powers of QAB. So at order QAB squared, this is what you get. You get a QAB squared times this factor. This 1 just comes from this bare term, and all of the work was to get this term here. So this is the correction. This term, this chi-log, is basically the Fourier, is the 0 frequency real part of the susceptibility I had earlier. And you can evaluate it in the SYK model. It's got a logarithmic divergence as t goes to 0. And notice the 1 over m. So at m equals infinity, this is not there. And that's why there's no spin glass order. This comes with a positive coefficient. But now you notice that no matter how large m, as t goes to 0, this term diverges. You know, this log divergence is just the Kramer's chronic Laplace transform of this discontinuity in the red line here. Comes from that. And so this thing eventually becomes negative at some temperature. And so they're always spin glass order at finite m. So this was something actually George Parkele and I pointed out in 2001. And it's part of the reason that we, didn't work that intensively on this model after that, because there was certainly an interesting SYK spin liquid with no spin glass order, but there was always a non-zero spin glass transition temperature where you got spin glass order. And you can estimate it now from the results, and it's, this is what it is for large N. It's exponentially weak for large N. But but I like to point out for M equals 2, this is still quite a small number. And in fact, now numerically, we also know this is very weak. So even though there is an instability, there's definitely a region, even for SU2, where you can clearly see this spin liquid behavior. So we want to understand what happens as we go across this line. What happened to the spectrum? Well, it turns out that's very, very simple to work out, because the only thing that's happening to leading order is a small QAB. So just add this term to these equations in the off-diagonal contributions and the diagonal contributions, sorry. And the only thing that appears for the fermions is QAA. So we just have to resolve the equation with this extra term over here. We can do that. And this is the basic result. So you have the spin glass order parameter at 0 frequency. And then at finite frequency, at large frequencies, you have this constant, the constant plus a graviton term, which is this term with this linear slope up here. But as you go to low frequency, and a frequency below omega star, which is equal to J times QA, this discontinuity in chi double prime omega vanishes linearly. And so there's a suppression of the very low energy density of states in the spin fluctuations, but there is a delta function at 0 frequency where all of those low energy excitations go. Okay. So in fact, in this model, there is always some spin glass order, although it's very weak. And we can understand what happens at higher frequencies. And there's a clear window in the numerics where you do see the spin liquid behavior, which is, and we have the full crossover. And really in this spin liquid, in this regime here, you're just talking about the spin glass state and its low energy fluctuations. And you can argue that those are essentially the confined fluctuations. There's no fractionalization here. So this is really a crossover, and it's a soluble model, a baby model of a gauge theory with finite density matter, where you can go from a deconfined state. This is sort of like the, if you wish, the quark-gluon plasma to a confined state, which would be the baryons. In this case, they appear as these spin glass states. Okay, and you can get an exact solution of this crossover, and I'm not aware of other problems where you can do that. Okay, very, very briefly, let me just mention, what we'd like to do is to make this TSG go to 0. And in this model, you can't do it. But you can do it by adding charged carriers. You can put in some electrons where these charges move around with some density. That's a whole different topic. I won't say anything more about it since I'm almost out of time. I refer you to this review article for more information on that. But let me just say that then you get a very exciting phase diagram when you add charge carriers. So far, I've been talking about this line where you use the spin glass order. But as you dope by around 2%, 20% doping, the spin glass disappears. You get an interesting quantum critical point. And this whole region is dominated by the SYK spin liquid behavior. And we have evidence for that all the way down to these very low temperatures. And if you look at charge transport in these regimes, you get beautiful Planckian metal type behavior. Anyway, so all of that I think is very exciting. And really the first solvable model where you have this kind of Planckian behavior, a universal Planckian behavior emerging at very low temperatures. But let me go back to the problem I was talking about, which is this SU2 spins with random exchange. So what we've seen is that there's this confinement of the SYK spin liquid at low temperatures. Now, one way we we're back to this problem. So one way we characterize the SYK spin liquid was in terms of its entropy. So at large NM, you get an entropy, which is in fact, which is this line here. It goes to extrapolates to a non-zero value at zero temperature. And this value was worked out by Georges Parquet and myself in 2001. This linear correction is a Schwarzian correction, first pointed out by Kittel and Maldacena and Stanford. So that's the behavior you get in the SYK model. Now in the SYK model, with the, as written down by Kittel and various generalizations, this is the behavior down to exponentially small temperatures, temperatures of order e to the minus n. In the SUM model, the spin model, it's only a behavior down to temperatures of order e to the minus square root of m. M, not n. And now we're interested in m equals 2. N, we're fine. We can send n to infinity, but we don't want to send m to infinity. So there is a temperature, the spin glass condition temperature, where this entropy actually goes down back to 0. So initially that sounds really bizarre. You had all this entropy, you had all these quantum states. What's happening to them? Why is the spin glass? I thought the spin glass had many, many, many states. Why don't I see that in the entropy? Well, the reason you don't see it is because what we're talking about here are pure states. In other words, what's happened in the spin glass, there certainly are many, many ground states, but those ground states are disconnected from each other. Once you fall into one valley, you never see the other part of it. So if you measure the entropy is a measure of the local valley that you're in. And there is no tunneling to all the other states. It's exponentially weak. And so you basically sit in one valley with whatever valley you happen to be in, because that will depend on all the history. And then you just see the entropy of thermal fluctuations and quantum fluctuations in that valley. So that's what's happening, down here. But once you're up here in the spin liquid region, something very different happens. You start quantum tunneling freely between all the valleys. And so you'll get a whole bunch of states whose spacing is very close to each other, but each one of them is a different linear combination of all these exponentially large number of valleys. And that's the physics, that's the quantum physics of the SYK entropy, where there's complete tunneling between all the valleys. Here, the valleys separate, and there's something called the complexity in the spin glass literature, which is a measure of the total number of states, or these total number of pure states. And that sigma c can be computed in this replica symmetry breaking theory. This is where you do need replica symmetry breaking to understand the complexity. And that, what we've shown is that this complexity, even in the zero temperature limit, is a finite number. Well, it's hard to compute it in our theory, but we can at least give a general route to computing it and showing that it's non-zero as t goes to 0. Okay, now what this complexity has to do with complexity that people are talking about in holography these days is an interesting question. It's obviously something measuring something very similar, but I'm not sure it's identical. All right, so finally, I'm a little bit, one more minute if I have the time. Let me just mention some work on holography. Starting with this paper of Maldacena, Michelson, and Strominger, where they call it anti-Hesiod fragmentation. And there's been subsequent work, especially by Anu and Frederick Denef, and also Felix more recently, that I learned about from Felix. So what, in certain models of gravity, Maldacena and Strominger found was that if you looked at a black hole, which has an ADS2 cross S2 horizon, in the limit of very large Newton's constant, I believe. No, large, yes. L Planck going to 0, yeah, okay. They found that there were many, many solutions where as you approach the horizon, there was a fragmentation of the horizon, and the charge of the horizon was split up into many small places. Okay. So, for example, they say here, unlike the higher dimensional case, the simplest approach, all finite energy excitations at ADS2 cross S2 are suppressed. Well, that's a correct statement, but if you include the boundary to the 5-dimensional geometry, then you have the Schwartzian. So that's, of course, something we understand better today, that you shouldn't just completely truncate it to AdS2 cross S2. You should also include the boundary fluctuations. But there was a separate instability here. They talked about whose existence really depends on the UV structure, which the horizon can fragment. So what we know today is that if you take the SYK model, this fragmentation is not present. The SYK entropy, this entropy here, this holds down to exponentially small temperatures, e to the minus n. There's numerical evidence for that. But if you take a different UV completion, which is this spin model, then there is a spin glass instability, and it certainly, smells like this fragmentation instability. And in fact, the connection between this fragmentation and spin glasses was pointed out by Anu and Denef and others, where they discussed a lot of this with papers that I don't fully understand. But anyway, they found multi-centered black hole solutions, which are extensively degenerate in supersymmetric theories. Okay. All right, so conclude, you presented I think one of the rare theories of finite density gauge charged quantum matter, where we can see a crossover from a deconfined liquid to a confining state. Now the deconfined state here is dual to the black hole with the AdS2 horizon. And there's intriguing set of ideas that the confining spin glass state has something to do with fragmentation of the horizon. So, thank you.
Okay, thank you very much for this nice presentation. We have time for a few questions. Is there any question here in the audience? Julian, there's a question.
Hi, Subir. I had a very simple question. Can you go back to that plot with the zero temperature entropy and the lack thereof? The one that you had recently, yeah. Just so I understand it, I mean, you said that they're all degenerate. Did I understand it correctly, or do you mean that they are just very small separation, like maybe exponentially small separation, all the ground states? Or is this
okay? So I presume you're talking about this here.
No,
so if you take
no, about your solid line actually. I mean,
over here,
of the two, but yeah.
The complexity. Yeah, I believe they have. Well, I think that they have exponentially close energies. Yeah, they're not exactly degenerate.
Okay, in both cases, right? So that's
yeah. I mean, there's this, I don't know if I don't think it's really known as exponentially close, but the way to precisely state it is that if you compute a certain entropy associated with this complexity, and then you take the large n limit first, and then you take the zero temperature limit or the zero energy spacing limit, then you get a finite value. But whether it's really exponentially small or not, I don't know, but it's certainly faster than 1 over n.
Yeah, okay, thanks.
Okay, I think there's no.
I mean, I think this will be an interesting question to address actually in spin glass state, in spin glass theory, and it's been difficult to address in the classical limit because then you have a discrete variable and you can't get, identifying what the states are is more complicated, strangely enough, classically than quantum mechanically. So I think there's some interesting open questions here and room for further progress.
Oh, hi, Subir. Sorry, just maybe a little bit of a follow-up to Julian's question. I just want to make sure I understand. So in the SYK model, there are also many very, exponentially finely spaced states down to.
Yes, yeah, correct. And that's governed by this entropy here.
Right. And so, but then in the spin glass phase, what's the distinction? I'm not sure if I completely got it.
Okay, let me try to. So you imagine you have all these valleys, multiple valleys here. Okay, so in the spin glass state, there are different states And in one spin glass state, you'll sit here, or you'll sit there, or you'll sit there, or you'll sit there, and there'll be small fluctuations here. Okay, so the entropy of these fluctuations is measured by S. The number of different minima is measured by the complexity. Now, what happens in the SYK state is, in fact, these are not the correct state. The states are some linear combination, different linear combination of all of these states. Okay, so you're exploring a much larger part of the phase space, and you get very different linear combinations, and they're all exponentially close to each other, but none of them are frozen in any given valley. They're in fact different linear combination of the many valleys.
So just to make absolutely sure I didn't misunderstand, in a given instantiation,
yes,
in the spin glass phase, one of those minima is going to be deeper than all the rest, and you sit
slightly deeper. Yes, that's related to Julian's question. That's correct. That's correct.
Slightly deeper, but that doesn't mean exponentially deeper, does it? Because otherwise,
exponentially, it could be the difference between this energy and this energy in the spin glass cake would be exponentially close to each other. But this barrier between them, the question is the barrier. It's really the barrier. These oops. Okay, let me draw it again.
But I think
so the spin glass, you have some phase space here, and you're sitting here in the spin glass state. What happens in the spin glass state is this barrier becomes exponentially large, becomes really huge. So you never go, you pick one and you sit there, even in a given set of Jij.
But sorry, I mean, I think what I'm confused about is why the Hilbert space consists of the direct sum of all of those possibilities, so that when you compute the total number of states, you sum them up and get the same answer. That's what I'm confused about.
Well, so it's a question of this pure state. So let's consider a much simpler model like a ferromagnet. A ferromagnet at low temperature has two pure states, spin up and spin down. And so when you're doing thermodynamics of the ferromagnet, you sit in a pure state, say spin up, and then you compute all correlation functions in that pure state. And that's how you define the thermodynamic limit in a pure state. And this pure state has a property that if you have some correlation function, S of x, S of 0, as x goes to infinity, this goes to S as x goes to infinity. Okay, so that's in a finite dimensional system. An infinite dimensional system is a little more subtle to define what a pure state is. And that is in fact part of what Parisi and others did. But anyway, so assuming the existence of these pure states, in more physical term, at least in my understanding, it means that you have some potential, and in the spin glass state, these barriers effectively become infinite. So if you pick a pure state, say you sit here, this is like picking all up spins in the ferromagnet. You will never ever go to any of those, because that's the n goes to infinity limit has been taken, the thermodynamic limit has been taken, so that you freeze into one of these values. Okay, so to understand the number of pure states, you have to kind of go beyond the thermodynamic limit. And the complexity then measures how many of these minima you have. On the other hand, in the SYK state, the physics is totally different. In the SYK state, these barriers don't go to infinity. You're exploring the whole thing. But the states are still exponentially close to each other because there's many different linear combinations. Okay.
Yeah, thanks. I think I understood it now. The entropy is defined here in the infinite n limit.
Absolutely, yes. All my discussion here is an infinite n, not infinite m, of course. Yeah, we're taking a thermodynamic limit, and the SYK model has a non-zero entropy in the thermodynamic limit followed by the zero temperature limit. You have to definitely take that order of limits. Whereas the spin glass does not. The spin glass, if you define the entropy in that way, when you take the thermodynamic limit, these barriers go to infinity. So you get stuck in one of these regions. And then your entropy vanishes as temperature goes to 0.
Okay, I think we have come to the end of this afternoon session. Let's first thank Subir once again for this nice seminar.